Alright, just wanted to make this short little video here about the Cauchy Schwarz inequality. And so basically I just wanted to make a short little video to kind of trace through this argument here. So the basic point of proposition 5.1.7 was that if we define the induced norm by the square root of the inner product of x with x, then number one, it defines the norm on V, and number two, the Cauchy Schwarz inequality, which is stated right here, applies. So we did this in class. That was fine. And then we started down the path of getting the Cauchy Schwarz inequality, and what we did was we noticed, first of all, that we could construct a complex number with modulus 1 such that lambda times the inner product of x and y was a real number, right? I explained you can basically take the, find e to the I theta, which is, basically the direction of x comma y as a complex number, and if you multiply it by e to the minus I theta, then that gives us a real number. So in view of that, we defined this q of t by the norm of t lambda x plus y quantity squared, right? Now because q of t is, make sure I'm on the, yeah, you can still see me. Because q of t is non-negative by construction, right, it follows that if we were to calculate the inner product of t lambda x plus y with t lambda x plus y, of course that gives us, that's just this by definition, well that has to be a non-negative real number. And that is pretty much all we need, as it turns out when we get into the details here, because as we work this out, right, we end up with t lambda lambda bar, and then this and that. Now, lambda lambda bar is, remember the length, basically, let me just write up here, we had, as I explained in class, basically we have lambda was equal to e to the minus I theta. So lambda lambda bar is e to the minus I theta times e to the I theta, which of course is just e to the 0, which of course is 1, right? So that gives us that the inner product, that's lambda lambda bar is 1, and of course we have t squared times the length of x squared, and then t times this quantity here, which I've called b, and that's a real number, and by the way that's also a real number, and of course that is the length of y squared. Now so we've got a quadratic, basically q of t is a quadratic polynomial with coefficients a, b, and c, and so great. And we also know that, as I was pointing out, if we look at the graph of q of t, right, if we were to graph q of t, I'll do it over here, right, if we look at q going up this way and t going that way, then the graph of q of t has to look, I mean, I don't know exactly where, it doesn't even have to, I guess I'm not sure it actually has to get to 0, but it could get to 0, but it definitely can't get lower than 0. So the point is that the discriminant, when we look at the quadratic formula for q of t, the the b squared minus 4ac, right, it has to be less than or equal to 0, because otherwise we'd have distinct real roots. Now this argument here, I'm just explaining that we can rewrite b as it, in particular, it works out to, as we go through the e to the I theta, e to the minus I theta business, and r was the length of the absolute value of x comma y as a complex number, that we end up with 2r, which of course is 2 times the absolute value of the inner product of x with y. Great. That's important to what follows. All right, so we need to have b squared minus 4ac to be less than 0, But b squared is 4 times the absolute value of the inner product of x comma y squared. And a was absolute value of x squared, and c was, I say absolute value, but I really mean the length of x squared, the length of y squared. And that has to be less than or equal to 0, but that is tantamount to saying that the inner product of xy is less than or equal to xy, which is, by the way, the Cauchy Schwarz inequality. And so that's the part that I couldn't quite fit at the end of class the other day. All right. So that's the proof, and yeah. And then, of course, once you know the Cauchy Schwarz inequality, it's easy to prove the triangle inequality. But there's a little bit more I'd like to talk about here in this short video, which is we can use the Cauchy Schwarz inequality to motivate a definition of angle. So if we're working over the real field, then we have, of course, the Cauchy Schwarz inequality, and so for x y not equal to 0, we have that the ratio of the absolute value of xy with the length of x times the length of y is less than or equal to 1. Well, that means that minus 1 is less than or equal to that, is less than or equal to that. Now I can say that meaningfully because the inner product of x and y is a real number. So I can make this inequality. And then trigonometry tells me that there's a unique theta between 0 to pi, for which cosine theta is equal to that ratio, and that is the standard definition of angle. If, like, for example, if we do dot product for the inner product, this is just the standard definition of angle between vectors in Rn. Now for a complex vector space, we can't quite do the same thing because the Cauchy Schwarz inequality is still true, but now the absolute value of the inner product of x and y is just it's a number, but it's a complex number, right? So the inner product of x and y is complex, so I can't just drop the absolute value here. So all I get is that the ratio of the absolute value of the inner product of x and y divided by the product of the lengths is less than or equal to 1. And like I said, I can't write an inequality just involving the inner product of x and y alone because we don't have a sense of ordering for the complex numbers, which plays well with the algebra of complex numbers at least. So all we have to do, all we can really content ourselves is saying this is unique, let's say theta tilde from 0 to pi over 2, for which cosine theta tilde is equal to that. Now, I say 0 to pi over 2, it's simply because if we look at the graph, of course, of this being, theta tilde, and this being, let's say, cosine theta tilde, it goes from, this is what cosine looks like there, right? So going from 1 down to 0, we can make it match like that, all right? That's the best I can do with the complex inner product. Now, I have some explicit examples over here. So there's my definition I've just explained. We define the angle between x and y to be theta, to be the unique theta from 0 to pi, for which that's true for a real vector space. We define the complex angle between x and y to be theta tilde, which is the unique theta tilde from 0 to pi over 2, for which cosine theta tilde is that ratio. Now, of course, word of warning, the complex angle is not a complex number, it's just a particular angle between 0 to pi over 2. And I call this the theta is the real angle, theta tilde I'll call the complex angle. And we can compare the meaning in a specific example, which I have down here. All right, so like x and y, 1 plus I, y, 1 minus I, 2 in complex 2 space. If I calculate the x comma y is, so I'm taking this vector and then I'm taking the complex conjugate that and then taking the dot product, I guess is my notation here, but that's 1 plus I plus 1 plus I times 2, which is of course 3 plus 3I. So that tells me the real part of that is just 3, which was our definition of the real inner product for the complex 2 space. On the other hand, inner product of x with x is 3, so that's that. Inner product of y with y is 6, so that's that. And so the real length of x in complex 2 space is root 3. The real length of y is, and by the way, the real and the complex length are both in agreement. They're both root 3 and both root 6 for this. And so like cosine theta tilde is the length of 3 plus 3i, which is the square root of 9 plus 9, which is 18, divided by the square root of 18. So cosine theta tilde is equal to 1, which means theta tilde is 0, whereas on the flip side of things here, the real angle between these two vectors would be given by 1 over root 2, which means that the real angle between them is pi over 4. So if you want to translate back into like the sort of natural correspondence to R4, these complex 2 vectors would correspond naturally to like 1, 0, 1, 1, and this one would correspond to 1, minus 1, 2, 0, as I have down here. All right. So these are the 4 vectors that naturally correspond to those 2 complex vectors. And if you calculate the angle between this and that in R4, you also get pi over 4. So there's pretty obviously an isomorphism between C2 and R4 at work here, namely this isomorphism. But in fact, it's more than an isomorphism. It preserves the angle between vectors as well as vector length. We call such a map an isometry. On the other hand, the angle between x and y in the complex sense is 0 because actually if you just multiply x by 1 minus I, you get y, which shows you that x and oopsie doopsies. Alright, fixed. That was supposed to be, yeah, come on. Well, I was trying to make a curly bracket there, but anyway. So this is a linearly dependent set because x is just, y is a multiple of x, right? Alright. In contrast, x comma y is linearly independent because these are not multiples in the real sense. So there is a difference between real and complex angle. And, you know, that's that. Now, so finally, here's just a sort of a more generic comment about real versus complex angle. Here I have x and minus x with x not equal to 0 in a complex vector space. They both have the same length, and the inner product works out to the length squared. So both of these ratios work out to 1. So that means that the angle between x and x, the complex angle between x and x is 0, and the complex angle between x and minus x is also 0. But of course, in the real inner product space, the angle between x and x is 0, whereas the angle between x and minus x is pi. So, you know, complex angle, a little bit weird. Definitely I don't have a good intuition for what complex angle is. But it's something you can think about and so forth. And finally, here's an actual definition for linear isometry. It's a mapping between inner product spaces with the same dimensions such that the inner product is transformed is preserved under the map rather. So like psi of x, psi of y in the image is going to be equal to the inner product of x and y in the domain for all x and y. That kind of map will preserve both the length of vectors as well as the angle between vectors. And having this sort of thing locally is what is the sort of basis for a lot of geometry in curve space. But anyway, more about that some other place. I think that's quite enough for now, for here. So thanks, guys.